we have a rocket that is in deep space and is initially at rest relative to an inertial reference frame and has a mass of 2.55 times 10 to the 5th kilograms, of which 1.81 times 10 to the 5th kilograms is fuel. The rocket engine is fired for 250 seconds while the fuel is consumed at a rate of 480 kilograms per second. The speed of the exhaust products relative to the rocket is 3.27 kilometers per second. We want to know what is the rocket's thrust, and after the 250 seconds of firing, what are the mass and speed of the rocket. So we saw that the thrust of the rocket, the force, which is the force of thrust, comes from the exit velocity of the exhaust gases multiplied by the rate at which fuel is burned. In this situation, we're given the velocity of the exhaust products, that is 3.27 kilometers per second, so we'll say 3.27 times 10 to the 3 meters per second. We're multiplying that by the rate at which that fuel is used up. Recall that was a derivative of mass with respect to time, and the rate at which the fuel is consumed is 480 kilograms per second. That's already in our base SI units. When we put all these together, we get 1.57 times 10 to the 6th newtons, or 1.6 meganewtons is the thrust that this rocket engine gives us. The next part is to find out what the mass of the rocket is after 250 seconds of firing and what the speed of the rocket is. We know that the initial mass of the rocket is 2.55 times 10 to the 5th kilograms. We know that we are burning up 480 kilograms per second, and we're losing, we're doing that for 250 seconds. So the change in mass will be the rate at which the mass is being used up multiplied by the amount of time. So in this situation, that will be 480 kilograms per second times 250 seconds. That is a change of 1.2 times 10 to the 5th kilograms. This is our change in mass, and we know it has to be a negative amount because the rocket is losing that mass as the engine burns up that fuel. That mass disappears, and so the mass afterwards, the new mass, which we'll give as a we'll say is a mass m. The new mass is going to be the original mass plus this change in mass. It's going to be 2.55 times 10 to the 5th kilograms that we had initially, minus the 1.2 times 10 to the 5th kilograms that we just burned. And we're left with 1.35 times 10 to the 5th kilograms. This is the mass of our rocket after we burned off a bunch of fuel. We burned off approximately 2/3 of the fuel that we had because we burned up 1.2 times 10 to the 5th and we had 1.8 times 10 to the 5th. If we want to know the velocity of the rocket at that point in time, we said that the velocity of a rocket is the velocity of the exit gases multiplied by the initial mass divided by the current mass. this current mass starts as being the same as the initial mass. At that point in time, at that first instant, the velocity is 0. And then as this mass gets smaller because that fuel is burned up, this gets to be a bigger number, which means the velocity increases up until all of the fuel is gone and you've reached a minimum mass. In this case, we have the velocity of the exit of the exhaust products. That was our 3.27 times 10 to the 3 meters per second. A logarithm is unitless, so we have to use meters per second so that we get out meters per second. And we'll multiply that by the logarithm of the initial mass of the rocket, which was the overall mass, divided by the current mass of the rocket. We see that the powers of 10 will cancel. And we get our velocity to be 2.08 times 10 to the 3 meters per second, or 2.08 kilometers per second is how fast our rocket is moving after it's burned off a large chunk of its fuel.